So from lessons 1 through 4, we've looked at oxidation states, half reaction equations, overall balance reaction equation, and redox titrations. Redox, as we know it, is the transfer of electrons. Since lesson 1, we've learned about oil rig. And so we want to be able to maximize the utilization of these electrons. So one way is to form voltaic cells, and this is what we will cover in lesson 5. From last time, we're able to see redox titrations of 3 kinds: iron with manganate, iodine thiosulfate, and the Wrinkler method. And now we're going to look into the electrical chemical cell, which is IB topic 9.2. 9.2 tells us that voltaic cells convert chemical energy to electrical energy, and electrolytic cells convert electrical energy to chemical energy. What this tells us is that redox, as we know it, is the transfer of electrons. Chemical reactivity and chemical reactions from redox are typically, if spontaneous, they're exothermic. So how can we utilize that exothermic release of heat? We can best do that by generating electricity. And that's what electrochemical cells are. Electrochemical cells are split into 2 types: voltaic cells and electrolytic cells. Voltaic cells generate electricity from chemical reactions. This means that the chemical reactions are typically spontaneous, and through the spontaneity, we're able to utilize the transfer of electrons to generate electricity. On the other hand, electrolytic cells are the opposite. So they drive chemical reactions by using electrical energy. And today we're going to look at voltaic cells. What are voltaic cells? So let's start with that. Some examples, what we use day to day: batteries. So batteries are types of voltaic cells. Battery that you use to also power a pacemaker in a patient's heart, or a battery for a car. My next question for you guys to just think about throughout this lesson is, are the batteries of different types of cars the same now, or are they different? So, for example, a gas-fueled car versus an electric car versus a hybrid car, are their batteries the same? Do they work in similar ways? Are they all voltaic cells, or are they not? Maybe think about that as we go through this. So now let's take a look at how we can make voltaic cells. We saw that from before in lesson 3 that zinc was able to act as a reducing agent in a copper reaction because of the reactivity series. Zinc was more reactive than copper. So from this reaction, we were able to figure out that the oxidation was the zinc reaction, and the reduction, the copper 2+½ reaction. We're able to generate electrical energy from this simple reaction because it's a spontaneous reaction and because heat is being released. It's an exothermic. So how the formula to creating a voltaic cell involves 2 half reactions we now call 2 half cells. These half cells, you attach an external circuit around the 2 half cells, and you can form a voltaic cell that runs a battery. For example, the zinc and copper, you immerse a zinc metal strip into its solution of its ions, and copper in its own solution of its ions, and you attach a circuit around the 2 beakers with a voltmeter, and the voltmeter will tell you the electric potential. So how do we make whatever you just saw? So let's go through the steps really quick. Step 1 is you put the metal strip into the solutions of its ions. The second step is the equilibrium through release or gain of electrons to form atoms or ions. There is something called the electrode potential, and this is called the charge separation. It's the charge separation between the metal and the ions in its solution. So for example, the zinc atoms can form zinc ions. This is when you put the zinc metal strip that you see into its solution. When you place it into its solution, it starts forming a half reaction equation of an oxidation half reaction. And from this, you can see that there are electrons forming at the surface of the zinc metal strip. And this also helps release the zinc from its metal to zinc 2+ ions. And when this happens, the metal strip becomes a little bit negatively charged because we now have electrons at the surface of the metal strip. And there's now a charge separation, and that's called the electrode potential. So there's a potential between the zinc 2+ ions that are floating in the solution versus the zinc that's on the metal. And we're able to calculate the electrode potential by running a small voltaic cell through that. So where would you think the equilibrium for the copper half reaction lies? So we know that zinc went through oxidation, and so more of its zinc 2+ ions are produced or released from its zinc metal strip. So the equilibrium lies towards the right, towards the products. Where do you think the copper half reaction would lie? So recall what we just went through. And try working this out. So now let's take a look. Where would the equilibrium lie for the copper reaction? In terms of the copper reaction, we can see that copper in the half reaction is the one being reduced. This means that the copper 2+ ions are becoming copper solids, right? Because copper has less tendency on the reactivity series to lose electrons compared to zinc, that's why zinc was able to displace the copper 2+. This also means that the equilibrium would lie further to the right. So if you wrote copper solid on the right-hand side, then the equilibrium should tend towards the right, tends towards the product. So let's continue. Now we have these two strips in their solutions. So some zinc atoms from the metal strip releases electrons and giving it a negative charge because we now have electrons at the surface of the metal. On the other hand, the copper ions in the solution accept these electrons, right, to form the copper solids from the copper rod, giving it a positive charge. So compared to the zinc metal strip, the copper and the copper solution, the electrode potential is more positive, has a higher electrode potential. And for the zinc, it's more negative, so it has a lower electrode potential. So lower, more negative electrode potential, we can see that the equilibrium tends towards the left, so it tends towards the ions for zinc. Higher positive electrode potential, we see that in terms of this half reaction, the equilibrium tends towards the right, so towards the formation of copper solid. Next, we connect the electrodes with an external wire, and the electrons flow from the negative electrode potential to the positive electrode potential. We call the negative electrode potential, when it's negatively charged, the metal strip, the anode. And when it's positively charged, we call it the cathode. And cathode on the right-hand side should be reduction, and anode should be oxidation, as we saw through zinc was oxidized and copper was reduced. So cathode, reduction, anode, oxidation. Electrons flow spontaneously from the anode to the cathode due to the potential difference. So the electrode potentials, because one is negatively charged and one is positively charged, that creates a potential difference. And that potential difference drives the electrons to move from the anode towards the cathode. And they go through the circuit. Step 5, we then add the salt bridge to complete the circuit. So the salt bridge, you would be able to see that the anions flow the other way. So anions flow towards from the cathode to the anode, and the cations flow from the anode to the cathode. And this is just talking about the salt bridge. The salt bridge consists of aqueous solution of ions. So these don't usually interfere with the reaction. The anions flow from cathode to anode, and the cations flow from anode to cathode. The salt bridge is used to balance out the charges and the potential difference. Otherwise, if the potential difference of the electrons keep moving from the anode to the cathode, then what happens is it keeps going on that side, and soon you're not going to have an electrode potential because it's all going to run out. So in order to balance and keep the circuit going, they need a salt bridge to displace that. So the anions flow the other way and the cations flow the other way. A voltaic cell converts the energy released from a spontaneous exothermic reaction into electrical energy. So that's what we covered in the beginning of this lesson. Let's take a recap. Step 1, putting in the metal strips. Step 2, we looked at how the metal strip played a role with its solution of its ions. And then we calculated the half reaction equations. From the half reaction equations, we figured out the equilibrium, which side it tends towards for each of the half equations. And then we were able to attach a circuit around the two beakers of two separate half reactions. And from that, add in a salt bridge to displace the potential difference. And with that, we're able to form a voltaic cell. Here is a shorthand cell diagram convention of what we just covered. So it usually flows from anode to cathode. So anode you would write on the left-hand side, cathode on the right-hand side. In the middle, the two lines mean salt bridge. The anode, they'll usually give you from the left to the right, so from zinc solid to zinc 2+ ions. And then the same thing from copper 2+ ions to copper solid. So that's why that's a reduction. And that's why the zinc to the zinc 2+ is an oxidation. The electrons flow this way via the external circuit. So it flows from anode to cathode, from oxidation to reduction. And the two half reaction equations in full are written down below. So now there's a question for you guys to work on. So would a zinc and silver voltaic cell have a similar or larger voltage than the previous zinc and copper voltaic cell? And why do you think that is? The hint for you is look at the increasing reactivity and look at the reactivity series and where the metals are placed on the reactivity series. And the second question for you guys to answer is, which direction would the electrons flow in a voltaic cell with copper and silver? So you would need to start with the different half reaction equations and figure out which direction the reaction favors, and draw out a voltaic cell labeled with the copper and the silver, either one on the cathode and one on the anode, and give it a shot.